back to my channel, and today I'm going to be talking about continued fractions. So let's begin by talking about the differences between a continued fraction and a regular fraction to essentially understand the essence of what a continued fraction actually is. Okay, so let's begin by talking about a regular fraction. Consider a regular fraction 1/4. Now 1/4 is going to be the fraction which we're going to be dealing with right now. Now we can write 1/4 as 25 over 100, 0.25, and 25%. There are many other ways to write 1/4. For example, 8 over 32, 2 over 8, 4 over 16, and so on and so forth. So these are some of the ways and most prominent ways in which we write 1/4. 1/4 can be written as 1/4 itself, 25 over 100, 0.25, and 25%. Okay. Now let's look at a continued fraction. This over here is a continued fraction. Now, as you can see, we do not use this in our everyday lives. This is precisely just going to be used mainly by pure mathematicians. And continued fractions are researched heavily in the 20th century and are still being used right now. And continued fractions are very important in the field of pure mathematics. But it's important to realize continued fractions still have an impact on humans every day. The approximation of pi, which we learn in school, which is 22 over 7, can be derived from a continued fraction of pi itself, and even more specific fractions or approximations for pi in terms of fractions can be taken from the continued fraction of pi. So as you can see, continued fractions are very useful. So in this video, our main goal is to essentially solve these four problems. But as you can see, they're divided by a line. The reason is because we want to be doing the straightforward method and the backwards method. What this means is we're going to be taking 27 over 23 and the square root of 3, and we're going to be converting them into a continued fraction. And over here in the backwards method, we're going to be taking the continued fraction, simplifying that, and take the square root of 3, and we're going to be taking the square root of 3's continued fraction form, and we're essentially just going to make it back into square root of 3. So we're going to derive the square root of 3 from the continued fraction. Okay, so let's begin by doing the straightforward section. Okay, so let's first solve 27 over 23. And we want to make this into a continued fraction. But before that, it's important to realize the format of a continued fraction impacts the continued fraction itself. Now, 1 over here, 2, 5, 3, 2, and 4. These are some of the numbers which are varied. Notice that for every numerator of the fraction, it's always going to be 1. So 1 over 2 plus 1 over 5 plus 1 over 3 plus 1 over 2 plus 1 over 4. The numerators of the fractions are always 1. That's a pattern that exists in every continued fraction. But as you can see, I've underlined 1, 2, 5, 3, 2, 4, and the numbers over here listed, and they can still continue on forever and ever. These can be varied, but the numerators of the fractions always have to be 1. We have to keep that in mind. The next is symbolism. It's important to realize that the first term over here can be written as 1 and then a semicolon. We can write a comma, which is also how you use it, but a semicolon just says that it's the first term of the sequence. Then we have to write next 2, and these are all one term, but we have 2, 5, these are the distinguished numbers, 3, 2, 4. And this is how this continued fraction specifically ends, but some go on forever. So this is how we write this in notation for this continued fraction. Now notice some of these numbers can be 1, like this is 1 itself. This can be 1, this can be 1, this can be 1, all of these can be 1. But when we're writing it, we have to write 1s in these positions. But right now, in this continued fraction, there isn't a 1 except for this. So we can just write it like this. Okay. Now, let's essentially find the continued fraction for 27 over 23. Now, we have to find the continued fraction for 27 over 23 strategically, using something called the Euclidean algorithm. So what is the Euclidean algorithm? The Euclidean algorithm is an essential important algorithm that's used for essentially in number theory. And essentially, the Euclidean algorithm also holds an essential important step to essentially finding the continued fraction for 27 over 23. Okay. So, first, we're going to say 27 is equal to 23 times some number plus the remainder. Now, 23 times a number, and that multiple is going to be a multiple of 23, and that should be the greatest number that goes into 27. That's obviously the number that's supposed to go there is 1, because 23 times 1 is 23. 23 is a multiple of 23, and 23 is the largest multiple of 23 that can go into 27. Remainder is going to be 4. Now we're going to take 23 and 4. We're going to state that 23 is equal to 4 times some number plus another number. Same method that we used before. This is going to be 4 times 5 plus 3. Continuing, we get 4 is equal to 3 times 1 plus 1. And then we get 3 is equal to 1 times 3 plus 0. We stop when it says 0, when this is at 0. Now we have to observe an essential key step. We're going to observe these numbers, 1, 5, 1, and 3. These are going to be the numbers which are used in our continued fraction. We can write it like this, using our notation. 1, 5, 1, and 3. Now, if we were to essentially be given a problem saying that find the continued fraction of 27 over 23 and write it in this format, most people would find this, then take this, then write it in the continued fraction, and then find it, and then group it back again and write it like this. So they take the Euclidean algorithm, get these numbers, write it in the continued fraction, find these numbers, and then put it back. But as you can see, these numbers will be the same numbers in the continued fraction. Now this is essentially distinguished from 27 over 23, so this is not equal to 27 over 23. But as you can see, this over here, we can just take these numbers, 1, 5, 1, and 3, and we can essentially deduce the numbers in the continued fraction. Okay, now let's actually write it into the continued fraction. So first number is 1. Second number is going to be 1 over 5 plus 1 over 1 plus 1 over 3. And this is going to be our continued fraction for 27 over 23. Now let's simplify this. So 1 is going to be equal to 3/3. Now 3/3 plus 1/3 is equal to 4/3. 1 over 4/3 is just going to be 3/4. So next we have 5 plus 3/4. Notice that we just solved this, then we took the reciprocal, now we're adding it to 5. This is equal to 20 over 4 plus 3 over 4, which is 23 over 4. Now we can take the reciprocal of that. That is going to be 4 over 23. And we get to 23 over 23. And we get 27 over 23. And this is going to be our answer. Now, the reason we had 23 over 23 is because 23 over 23 is the same thing as 1. And we got 27 over 23, and this is essentially the continued fraction for 27 over 23 itself. And we can write it like this. Okay, so let's write this over here. The answer for 1 is going to be 1 plus 1 over 5 plus 1 over 1 plus 1 over 3. And this is going to be the answer for number 1. Let's just also write it in the notation format. So we'll write over here, this is just going to be 1, 5, 1, 3. Okay. That is going to be our answer for number 1. That's the continued fraction for 27 over 23. Now let's look at a harder problem. Square root of 3. Now the square root of 3 is the square root of 3. As you can see, it's kind of going to be going on forever and ever and ever. That's the square root of 3. And it looks complicated. And indeed, we do not use the same steps as we use for 27 or 23. Rather, we use a whole different type of method. So it's important that we do this carefully because it involves a lot of algebra and algebraic manipulations. Okay, so consider the square root of 3. Now we're going to be using the square root of 3 in this case. Now we're going to set x sub 0 equal to the square root of 3. And we're going to state that a sub 0, or the floor, well, a sub 0 specifically, is going to be the floor of x sub 0. So these are two definitions which we define. Now, we're also going to define that there's going to be a pattern, which we'll just write x sub 1 is equal to 1 over x sub 0 minus a sub 0. X over 2 is equal to 1 over x sub 1 minus a sub 1. And you can see the pattern going on forever and ever and ever. Now, what this essentially tells us to do is that we're supposed to take all the a values, and we're essentially supposed to construct it into the notation over here and into the continued fraction. And that's essentially what we're supposed to do. And we have to continue doing that till we see a pattern, till we have a good approximation, or to see if it's finite. Now, in this case, there's going to be a lot of terms, and probably it's going to be infinite, so we're just going to be stopping at a few terms. Okay. Or once we've identified a pattern, we will just put dot 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 to signify that we know there's a pattern in this. Okay. So let's first find what a sub 0 is, because a sub 0, a sub 1, a sub 2, a sub 3, etc., they're the most important parts in the continued fraction, because they're going to be these numbers, 1, 2, 5, 3, 2, 4. They're going to be the numbers representing those positions. Okay, so let's first find and talk about what the floor function is. So what is the floor function itself? The floor function is essentially just rounding to the closest integer that's lesser than it. So for example, take 3.5. It's tempting to say it's 4, but we're going to round to the closest integer that's below it. So 3.5 is just 3, 3.7 is 3, 29.37 is going to be 29. 29.37654 is going to be 29. 32.79421 is going to be 39. So etc. So how it's going to be like that is if we take a number, we're going to find the closest integer that is below it. So that's what the floor function is. Square root of 3 has a decimal format. So many people might think that we have to use a calculator, but rather we can be smart about this. Square root of 2 is about 1.4 and etc. Square root of 4 is about 2. Well, it is 2 essentially. Square root of 3 must be between square root of 2 and square root of 4, so it has to be 1 point something. So if we floor that, we're just going to get is equal to 1. So let's write our notation. So 1, we've got that. Now let's find x sub 1. So let's work out x sub 1. X sub 1 is equal to 1 over x sub 0, which is square root of 3, and then minus 1. Now we have to essentially manipulate this so there's no radicals at the bottom, because this gives us a clearer perspective. So essentially we're rationalizing the denominator. Okay. So we're going to multiply by square root of 3 plus 1 over square root of 3 plus 1 to get square root of 3 plus 1 all over 3 minus 1. This is going to be square root of 3 plus 1 all over 2. Now that's essentially what x sub 1 is going to equal to. X sub 1 is going to equal to square root of 3 plus 1 over 2. So let's just write that. X sub 1 is square root of 3 plus 1 over 2. Now you also might think, okay, this is a little bit more complicated. We definitely need a calculator. But we can also solve this without a calculator itself. Square root of 3 is going to be 1 point something. Adding 1 to that is going to be 2 point something. Divide by 2, that's going to bring us to 1 point something, which flooring that gives us, obviously, just 1. So we know that a sub 1 is just 1 once again. Now you might be tempted to think it's going to be 1, 1, 1, 1, 1, 1. And in some situations it is, but in the square root of 3, it's not. Okay, so keep that in mind. Let's work out x sub 2. X sub 2 is equal to 1 over x sub 1 minus a sub 1. So x sub 2 is equal to 1 over square root of 3 minus 1. So, well, square root of 3 plus, well, it's going to be square root of 3 plus 1 over 2 minus 1. This is what it's going to be. Now, we can write minus 1 to be minus 2 over 2. To therefore get 1 all over square root of 3 plus negative 1 all over 2, which will just write 1 over square root of 3 minus 1 over 2. Now we can take the reciprocal of that to just say it's 2 over square root of 3 minus 1. And this is where we have to use a little bit of algebraic manipulation. So let's just draw this up here. We have the square root of 3 minus 1. And this is 2 over square root of 3 minus 1. And we're going to write this to be 2 times 1 over the square root of 3 minus 1. So square root of 3, 2 times 1 over square root of 3 minus 1. Well, what's that going to be? Well, square root of 3 minus 1, or 1 over square root of 3 minus 1 specifically, can be written as square root of 3 plus 1 over 2. We've already just seen that. If we multiply that by 2, we're just doubling the value. So we substitute that, we're going to get 2 times square root of 3 plus 1 all over 2. These cancel to just get square root of 3 plus 1. And if square root of 3 is just 1 point something, adding 1 will give us 2 point something, which means that the floor of that is going to be just 2. So we can write that over here. X sub 2 is equal to square root of 3 plus 1, and a sub 2 is just going to equal to 2. We can write that here. Okay. Now let's solve for x sub 3. Okay, so we have x sub 3 is equal to 1 over x sub 2 minus a sub 2. Substituting, we get x sub 3 is equal to 1 over x sub 2, which is square root of 3 plus 1 minus 2. This gives us x sub 3 is equal to 1 over square root of 3 minus 1. But if you think about it, that's what we had at the very beginning. Let's just work it out just in case, even though the algebra is going to be the same, and it's 100% going to be square root of 3 plus 1 over 2. Let's just check out our work. Let's just see if we've got this right. And you also might be wondering, why are we multiplying by square root of 3 plus 1 over square root of 3 plus 1? And you've also might be also wondering, if we do multiply by that, should we multiply it to the other side? Because that's what we're learning in algebra. Both sides have to be equal. But if you think about it, square root of 3 plus 1 over square root of 3 plus 1 just simplifies to 1. So this is going to be very simple. So, and this is also going to be very simple because when we're multiplying this simplifies, so there's not any radicals in the denominator, and moreover, it's just going to give a neater form. And we're just multiplying by 1, essentially. So we got square root of 3 plus 1 all over 3 minus 1, which is just going to be square root of 3 plus 1 all over 2. So yes, x sub 3 is going to be square root of 3 plus 1 over 2, and a sub 3 is going to be a sub 1, which is just 1. Okay. Now if we think about it, we're going to see that x sub 4 must equal to x sub 2, and a sub 4 must equal to a sub 2. But we still don't know that, so let's just check to see if there's a pattern that's arising. Okay, so we have x sub 4, which is equal to 1 over x sub 3 minus a sub 3. X sub 4 is equal to 1 over square root of 3 plus 1 over 2 minus 2 over 2, which is equal to 1 over square root of 3 minus 1 over 2, which can be said to be 2 over square root of 3 minus 1. And now, using the same technique we used earlier, this is 2 times 1 over square root of 3 minus 1. And we've seen that square root of 3 minus 1 is just square root of 3 plus 1 over 2, which brings us to say that this is 2 times square root of 3 plus 1 over 2, in which we get square root of 3 plus 1. And is this x sub 2? Yes, it is. Square root of 3 plus 1 is definitely going to be equal to x sub 2. Okay. So x sub 4 is going to be equal to square root of 3 plus 1. Now, square root of 3 plus 1 is going to equal to square root of 3 plus 1. So x sub 2 is equal to x sub 4. Now, reducing, we get a sub 4 is going to equal to a sub 2, which is just 2. So we can write that down. So we also have to write down a sub 3. So that's going to be 1, and that's going to be 2. And we see this extends forever. And we find an essential pattern, which we have over here. We find that it goes 1, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, etc. So we can essentially write this into a fraction, a continued fraction. And essentially write the dot, dot, dots, just to say it goes forever. So let's write it. So you have 1 plus 1 over 1 plus 2 over 1 plus 1 over. So you have 1, 1, this is supposed to be 1, this is supposed to be 2, 1, 1, 2, 1 plus 1 over 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2. And it goes dot, 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 dot. So I just check it. 1, 1, 2, 1, 2. This is a 1. 1, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. This is also 1. Okay. So as you can see, this is going to be equal to the square root of 3. And this is the continued fraction for square root of 3. And it's kind of amazing how the square root of 3 in a continued fraction doesn't even use 3 a single time. It uses just 2's and 1's. Okay. Now that we've talked about that, and we've observed what the square root of 3 is itself, we can make a summary, because in the next video we'll talk about how to go backwards, how to simplify this, and go backwards from the square root of 3. So let's summarize, and then we can make this video to an end. Okay, so when we're talking about continued fractions, we always have this specific format. The numerators are always going to be 1's, and the denominators can also vary. For example, we have 1, 2, 5, 3, 2, 4, and over here we have 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and etc. And they can be 1 itself also. And we also learned that 27 over 23, we can use the Euclidean algorithm to essentially find the continued fraction. But for the square root of 3, we have to use a different method, in which we state that there's an a sub 0, or a sub 1, or a sub 0, and we state that they're equal to the floor function of x sub 0 and x sub 1, depending on where you're starting from. If you say x sub 0 is your base, then you can start from x sub 0. If you're starting from x sub 1, you can start from x sub 1. Depends on where we start from. In this video, we started from x sub 0 and a sub 0. But as you can see, there are a variety of methods to do continued fractions. These are some of the 2 most prominent methods. In the next video, we'll talk about how to simplify this and how to take this continued fraction and deduce that we have the square root of 3. Now that we've talked about that, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.